Hey, welcome back. So here's our instruction time together. I'm going to help you understand about rational functions. What is a rational function? Remember, yesterday we talked about reciprocal functions that look like y equals 1 over x plus 2. Okay? Or we had y equals 1 over, or we could have 2 over x minus 3 plus 4. Okay? Those were reciprocal functions. These are the simpler forms, a subset of rational functions. Now we're going to have a polynomial over a polynomial, like that. And we're going to look at some key characteristics to help us graph it. We're going to use Desmos to sketch it, but we're going to identify the key components that Desmos doesn't give us. Okay, functions that have polynomials in both the numerator and the denominator, that's a rational function. The domain is going to be any real number except, circle that word except. Except the values that make the denominator become 0. Super important that you understand that phrasing. Okay, so we have to look at the denominator and figure out the x values that make it equal 0. Those have to be excluded from the domain. So is there anything that I can plug in to the denominator of here that's going to make it equal 0? Well, I would get x squared equals -1, and we know from our complex numbers that that is equal to plus or minus I. Are those real? Are those real? No. So this one is just all real numbers. All x's such that x is real. Okay? Just like that. That's set notation. We're not going to use interval notation on it because as the number of points you have to exclude gets higher, the interval notation gets kind of crazy. On number 2, we have y equals x plus 3 times x plus 2 over x plus 2. So let's check and see what's going to make our denominator equal 0. Well, that's going to be -2. So that means that I can't plug in a -2 because then I would be dividing by 0. So my domain, all x's such that x cannot equal -2. Why don't you try 3 as your video question and come on back. All right, x minus 2 equals 0, x is equal to 2, so this is all x's such that x cannot equal positive 2. Remember, we're finding the ones that it cannot equal. Okay. So there are several key characteristics that while we're going to use Desmos to get the sketch, it doesn't tell us this. It expects us to know it. So we have to figure out, we have to learn what they are. The first most important point is called the point of discontinuity, and it is directly linked with the domain. It is any value of x that causes the denominator to become 0. So the first thing that you want to do when you approach a rational function problem is to factor both the numerator and the denominator. Factor both the numerator and the denominator. Okay? Once you do, then you can look at your factors in the denominator and you can decide whether you have a removable discontinuity or a non-removable discontinuity. Okay, we're still talking about discontinuity. There's two types. Removable and non-removable. The removable creates a hole, and it's caused by the same factor in both the numerator and the denominator. So when you factor, if you have an identical factor in both the numerator and the denominator, that's going to create a hole or a removable discontinuity. Okay? So if I factor this, I get x minus 4, x plus 1, all over x minus 4. Do you see how I have the same factor in the numerator as I do in the denominator? that's going to create a hole. A hole. You literally, you have a line, and somewhere on this line, you have a physical hole. Okay? Now, non-removable discontinuity is creates a vertical asymptote. It creates a vertical asymptote. Okay, we know what those are. We've done them in exponentials. We've done them in logs. We've done them in logs. We've done them in reciprocals. Okay, exponential had a horizontal asymptote. And this is caused by any factor in the denominator that doesn't have a matching factor in the numerator. So let's factor this one, and I get this stays the same. There's nothing to factor out of that one, and this becomes x minus 3 times x plus 1. Okay, so in order for a factor to be the same, term by term, sign by sign. So see how this is x plus 3 and this is x minus 3? They can't cancel. Okay, so think about it can't cancel. CC, can't cancel. Okay, so now we're going to have vertical asymptotes at x equals 3 and x, oops, sorry guys, should be a negative 1. And x equals 1. Okay? Should be a vertical asymptote at x equals 3 and x equals 1. This one up here, we have a hole at x equals 4. I set my denominator equal to 0, and that's where I have a hole at x equals 4. And then to find out its height, all I have to do is plug it back into the remaining factor, and it'll tell me how high up that hole occurs. Okay, so let's watch here. So now we're going to talk about finding an x-intercept. So you're going to use the factors in the numerator. Okay, but here's what you have to be careful of. It cannot have a matching factor in the denominator. Do you see how you have an x minus 4 here and an x minus 4 here? Well, this is saying that x can't equal 4, so there's no way to have an x-intercept at 4. So I'm just going to set my remaining factor equal to 0. So x plus 1 equals 0. So x is equal to negative 1. So my x-intercept is the point negative 1, 0. Y-intercept, you can find it a lot of different ways. You could plug in to your original. You're going to always plug in for 0. This is key. You're going to plug 0 in, you're going to plug 0 in for x. We're going to plug 0 in for x. So we get y. Y is equal to 0 minus 4 over 0 minus 4. Okay, so I just get negative 4 over negative 4. So I get the point 0, 1. Okay, look here. In this form, it's always going to be the constant divided by the constant. Okay? In this form, when it's factored, you can still find it. You can still do the same thing. You're going to get 0 minus 4 times 0 plus 1 over 0 minus 4. Okay? And when you do this, you're going to get negative 4 over negative 4, and you still get 1. So this is the point 0, 1. Two different ways of doing it. Okay? All right, the next characteristic is the vertical asymptote. Vertical asymptote is a non-removable discontinuity. How did we find that? By setting our factors in the denominator equal to 0. These factors are the ones that don't have a match in the numerator. Okay? So do you see how I start with y equals x plus 3 over this polynomial. The first thing I did was factor this polynomial, okay? So I have to set both of my factors in the denominator equal to 0. So I get x minus 3 is equal to 0, and x minus 1 is equal to 0. So this says x equals 3 and x equals 1. Your vertical asymptotes are going to be the lines x equals 3 and x equals 1. Notice how I distinguish between a line and a point. That's why it's so important for you to know when you're talking about a point and when you're talking about a line. The domain, we talked about it. It's all the real values of x except what makes the denominator equal to 0. You must exclude all of the points of discontinuity. You must exclude all of the points of discontinuity, whether it be a whole or a vertical asymptote. So you want to go back to your original factored form before you canceled anything out. Okay, so in this one, this is x equals 3. It makes the denominator 0. This is x equals 1. So watch how we write this. The domain, all x's, such that x cannot equal 3 or 1. X cannot equal 3 or 1. Okay, that's the domain. On this one, this is all x's such that x cannot equal 4. Okay. All right, so let's go through one of these. The first thing when you approach these problems is that you want to factor. This one was done for us. How nice. This is done. Now, once you're factored, you want to look at points of discontinuity. So wholes are going to be caused when you have a matching factor in the numerator and the denominator. Do I have any matching factors? Y equals x plus 3 over 2x plus 3 times x minus 1. Do any of those match? No. So both of these are going to create vertical asymptotes. So you have 2x plus 3 equals 0, 2x equals negative 3, x equals negative 3 halves. X minus 1 equals 0, x equals 1. Those are your vertical asymptotes. You can go ahead and mark those on your graph. The domain stems right out of those points of discontinuity, right? These two are super connected. That's why in my mind when I go through this, I find my points of discontinuity, then I automatically write my domain. All x's such that x cannot equal any vertical asymptote or any whole. I don't have any wholes, so I just have to include my vertical asymptotes. Negative 3 over 2 and 1. My x-intercept is any factor in the numerator that can't be canceled with 1 in the denominator. So x plus 3 equals 0. Set it equal to 0. X equals negative 3. So it is the point negative 3, 0. The y-intercept, I plug in 0 for x, and I get 0 plus 3 over 0 plus 3 times 0 minus 1. So my numerator is 3, my denominator is negative 3, so I get the point 0, negative 1. That's going to be my y-intercept. And now what I'm going to do is I've plugged it into Desmos and I'm going to bring it in. And now what we're going to do is we're going to fill in any points of discontinuity. Okay, so you look for wholes and look for non-removable vertical asymptotes. And then and we'll do horizontal asymptotes in just a second. So I have to mark with a vertical line, and I'm going to choose red. Mark with a vertical line these two vertical lines. X is negative 3 halves. So here is negative 1. So this line here is negative 3 halves. Okay. and then x equals 1. Here's the line x equals 1. And then if I had a hole, I would find the height of the hole by plugging it in and to my remaining factors, and then putting a hole at that height in that location. Okay. All right. We're going to identify the key characteristics, and then we're going to use Desmos to help us graph it. So factor it. I have to factor, I'm going to go up here to factor it. This is x plus 2, x minus 2. And this is 3 times x minus 2. So now I'm going to transition my thoughts to points of discontinuity, removable hole. Do I have the same factor in the denominator and in the numerator? I do. So that's going to create a hole. X minus 2 equals 0. Set it equal to 0. So x is equal to 2. That's where your hole is, okay? So now to find the height of the hole, here's what I'm going to do. I'm going to plug it in to what's left of my expression after I cancel those factors out. So I'm going to get 2 plus 2 divided by 3 is equal to 4/3. So my removable hole is going to be at 2, and then the height is 4/3. Because we're going to want to mark that on our graph. The non-removables are caused by any factors in the denominator that can't be canceled. Do I have any of those? No. No vertical asymptotes. Okay? All right. My domain is any point that I have to exclude, whether it's a hole or a vertical asymptote. So I have all x's such that x cannot equal my hole, 2. The x-intercept, I pick up any factor in the numerator that can't be canceled with the denominator, and I set it equal to 0, so x is equal to -2. So that's the point -2, 0. My y-intercept, I plug in 0 for x, so I get 0 minus 4 is equal to 0 minus 6, so I get 4 over 6, which is equal to 2/3. So I get the point 0, 2/3. And then we're going to sketch using the Desmos. Okay, so here's what I have. Isn't that interesting? If you look back up here, this can be simplified and written in an equivalent expression of x plus 2 over 3. So you get a line. The only thing is that this line in Desmos doesn't tell us this. It expects you to know that at x equals 2, I'm going to have a hole at 4/3. So I have to put a hole right there. Literally, you have to make a hole in your sketch, okay? Like I can't erase the blue line, but you want to erase that blue line, okay? All right, let's try this one. We have y equals x squared plus x minus 6 over x squared minus x minus 2. I'm going to factor first. So this is going to be x plus 3 over x minus 2. Got to get this part right, guys. And then this one is x minus 2 over x plus 1. The next thing on my radar should be points of discontinuity, removable holes. Okay, do I have any removable holes? Yep, I do, here and here. So that's going to be at x minus 2 equals 0. So at x equals 2. If I plug that into the remaining factors, I get 2 plus 3 is 5 over 2 plus 3 is, 2 plus 1 is 3. So this is going to be a removable hole at 2 and then 5/3. My non-removable, these are going to create the vertical asymptotes. See how I cannot cancel the x plus 1? So that means that x plus 1 equals 0. So that means x equals negative 1. That's a vertical line at x equals negative 1. The domain can be any x except whatever creates a hole or a vertical asymptote. So I'm going to say except x cannot equal negative 1 or 2. My x-intercept, I look at whatever factor remains up here in the numerator and I set that equal to 0. So x is equal to negative 3, 0. My y-intercept, I plug in 0 for my x's, and when I do that, I get 0 plus 0 minus 6, so that gives me negative 6 over 0 minus 2, so that gives me 3. So my y-intercept is at 0, 3. And now I'm going to bring up my Desmos, okay? And then I have to put in my holes, and it's a good idea to mark our x and y intercepts as well, and our vertical asymptote. So my vertical asymptote is going to be here at x equals negative 1. Okay, then I have a hole at x equals 2 and then 5/3. So I'm going to put in a hole here. See, I put in a hole there. You have much more accuracy than I do. And then I'm going to mark my x-intercept is at negative 3, 0. So you're going to want to put a dot there. That's a closed dot. And then my y-intercept is at 0, 3. So put a closed dot there. Sorry, I have a hard time. There we go. Just like that. All right. So that's going to be where we're going to get through for tomorrow's daily assignment, and then we're going to talk about horizontal asymptotes and putting those in the graph for the second day. So I'm going to make this one video, but we're going to stop at slide 8. Horizontal asymptote, we talked about this with the exponential function. And for a rational function, it is linked to, it depends on, you have to understand, you have to know the relationship of the degree of the numerator to the degree of the denominator, okay? So we have to remember how to find degrees, all right? So you're looking for the highest appearing exponent in the numerator. So on this one, this is a 1. Over the highest appearing exponent in the denominator. Not over, just you're comparing it, okay? All right, here my highest appearing exponent in the numerator is 2. My highest appearing exponent in the denominator is 2. My highest appearing exponent in the numerator here is 2. My highest appearing exponent in the denominator is 1. So I want you to take a minute and make sure that you can determine the degrees of the numerator and the denominator. Okay, so try the video questions. Okay, now here's where the comparison comes in. Now that you can find the degree of the numerator and the degree of the denominator. If the degree of the numerator is less than, smaller than the degree of the denominator, your horizontal asymptote is always going to be y equals 0. So in this case, the degree of my numerator was 1. The degree of my denominator is 2. So my horizontal asymptote is going to equal or be y equals 0 because the degree of my numerator was smaller than the degree of my denominator. If you have the degree of the numerator equal to the degree of the denominator, if the degree of the numerator is exactly the same as the degree of the denominator, Then you're going to look at the leading coefficients. Remember, your leading coefficients are the numbers in front of your highest degree. So this would be 2 over 1. And that's what your horizontal asymptote is going to be. Y equals 2 over 1 or y equals 2. If the degree of your numerator is bigger than the degree of your denominator, then you don't have any horizontal asymptote. So you would say HA, not 0, but none. There isn't one. There isn't one. Okay, so let's kind of put all of this together, okay? So here's what I do. Because I have the horizontal asymptote depends on the degree in the numerator and the degree in the denominator, I want to look at it before I factor and cancel anything out. So what is the degree of my numerator? 2. What is the degree of my denominator? 2. So now I'm going to look at my leading coefficient and divide it by my leading coefficient. So y is equal to 1 over 1. Okay? It's not 1 because these two are the same. It's 1 because the leading coefficient of the numerator over the leading coefficient of the denominator is equal to 1. So I have y equals 1. Okay? Oh, I didn't want that to come forward. Oh, well. Now we're going to factor. And so we get y is equal to x plus 3 and x plus 1 over x minus 5, x minus 1. Okay. Holes. Do I have any removable holes? Do I have any factors that match the denominator and the numerator? Nope. So no holes. Do I have any vertical asymptotes? Yep. X minus 5 equals 0. So x equals 5. X minus 1 equals 0. So x has to equal 1. And those are my vertical asymptotes. Let's switch. So at 5, here's 5. And here's 1. I'll put those in. My domain is going to be every x except any of my points of discontinuity. I don't have any holes, but my vertical asymptotes I have. So x cannot equal 5 and x cannot equal 1. My x-intercept, there's going to be 2 of them. X plus 3 equals 0. So I have negative 3, comma 0. And then x plus 1 equals 0. So I have negative 1, comma 0. So I'm going to plug in here. I have to make an x because I can't get him that close. And then negative 3, 0. Okay. My y-intercept is going to be 0. I'm plugging in 0 plus 3, so I get 3 over 0 minus 0 plus 5. So I get the point 0 3/5. So 0 3/5. Okay. And then I sketched it. And here's what I want to point out on this particular graph. Remember how we have a horizontal asymptote at the line y equals 1? Let's draw that in. And you think, hey, what's going on here? Because I thought I couldn't cross my horizontal asymptote. Okay, here is the fine innuendo. Your horizontal asymptote, it's targeting, you have to think about what's happening out at the extremes, out where x goes to negative infinity and x goes to positive infinity. That's where it's not going to cross. It could cross close to the origin, but as we go further and further out, this graph here is going to approach. It's going to get closer and closer and closer to that line y equals 1 from underneath it. And of course, this one is going to go out as well. Okay, so just be careful how you actually think through that. All right, here are assignments for a couple days, and thank you for listening, and I will see you tomorrow.